MIT Club of Northern California. We'll give it a few minutes for everyone to join the session. It's a popular session, and we're really excited to welcome some very esteemed guests from the SETI Institute. But I'll give it a few more minutes. And in the meantime, I just wanted to share that the lifelong learning track is a track where we're opening up to different knowledge experts to share about what they've been researching or what they've been thinking a lot about. One of the motivations behind this is that there are so many questions from MIT alums about where can I learn more about certain subjects, and there's an innate curiosity among our community. And so we wanted to open up this forum to be able to engage in some of these knowledge exchanges. And if you're interested in getting involved and sharing your knowledge or helping host knowledge and hosting experts in various areas that you're interested in, please feel free to contact me at xwzhang@alum.mit.edu. Was I on mute the whole time?
No, we could hear you.
Oh, can you hear me now?
Yes.
Yes.
Oh, okay, perfect. Okay, so all right, we'll give it a few more minutes. But yes, so if you are interested in getting involved, please feel free to email me. And just a quick overview for those of you who don't know about the MIT Club of Northern California. What is a mission for MIT CNC? It's to further the well-being of local MIT alumni by connecting them with each other and with MIT. We do this by being volunteer-led, so all of the officers are volunteers. We're organizing unique events and programs. We're supporting lifelong learning and nurturing continuing relationship with MIT while supporting MIT's mission to serve the nation and the world through science and technology and make a better world. And I'm not going to go into this in detail, but there are a number of different programs, and you can check out more of this at www.mitcnc.org. And wanted to open up our talks with Bill Diamond, who is the CEO of the SETI Institute and a very, very exciting speaker, as well as supporter of sciences. And it's a very interesting person that I've gotten to know over the past year. And one thing that I want to share is, I think like many of MIT alums, I first learned about SETI maybe 20 or close to 30 years ago. And I've been in love since. And for those of you who don't know, SETI is actually just in our backyard in the Bay Area. And I was thrilled to get to meet Bill and to learn that the Institute is here. So I'll pass it over to Bill to share more about the Institute.
Great. Well, thank you very much, Wendy. And I hope you haven't oversold my capabilities here, but we'll give it a shot. It's wonderful to be here, an honor to speak to all of you from the MIT community, and especially here in the Bay Area. Maybe there's some of you from elsewhere in the country, but having grown up in the Boston area and been born in Cambridge, there's a little bit of MIT that runs in my blood as well. And actually, very interestingly, one of our trustees is Dava Newman, who not only has the distinction of being the deputy administrator at NASA during the Obama administration, but is a professor of aeronautics and engineering at MIT, and was most recently named as the new head of the MIT Media Lab. So we've got some additional connections there as well. And it's great to have had the opportunity to meet with Wendy and to have the opportunity for all of you to get to meet the SETI Institute a little bit. So I'm going to give you a quick overview of the Institute, a little bit about who we are, what we do, how we're organized. And then I'm going to turn it over to the far more interesting part, which is to hear from some of our research scientists and affiliate researchers at the Institute to talk about their specific work. And that includes work in education programs as well as our research domains. So without further ado, I am going to share my screen and see if I can get us going with a little introduction. right, so hopefully that is working. Wendy, you can give me a thumbs up if you see everything clearly there. Terrific.
Yes.
All right, so let's meet the SETI Institute. So at the SETI Institute, we have kind of a different, let me just get my mouse back in control here, a somewhat different mission statement and vision statement than other organizations. But the vision at the Institute is to inspire and unite humankind through exploration and discovery as the archaeologists of our future. And our mission is quite simply to lead humanity's quest to understand the origins and prevalence of life and intelligence in the universe. That's the mission of the SETI Institute. So we have a structured approach to address what is essentially a singular science question. And that science question is, are we alone in the universe? So we address this question within three fundamental domains of research: the structure of the universe, planets and habitability, life, complexity, and intelligence. These domains are then investigated through 6 individual branches of research, which are astronomy and astrophysics, exoplanets, planetary exploration, astrobiology, climate and geoscience, and of course, last but not least, radio and optical SETI, or the search for technosignatures as a proxy for life and intelligence. We have over 140 research scientists at the Institute and affiliates who come from about 23 different and distinct academic and research backgrounds, and pretty much cover what I consider to be nearly the full spectrum of the natural sciences. So our work includes NASA science mission support, field expeditions, laboratory research. We use ground-based observatories, both in the radio and optical domains. We use space-based observatories, including Hubble, Kepler, TESS, Cassini, et cetera. We also do technology and instrumentation develop. In fact, a instrument on the Curiosity rover called the ChemMin system, which is an X-ray diffraction instrument that does elemental analysis of Mars regolith, was developed by a scientist at the SETI Institute and a colleague at NASA Ames Research. We explore basically to understand the structure of the universe, planetary environments and habitability, the nature and origins of life, and the evolution of intelligence and technology. Yeah, mouse frozen. So a typical day at the office includes science support for NASA missions like Cassini, Kepler, Curiosity, New Horizons, and others. Institute scientists have been involved in nearly every unmanned NASA science mission since Voyager. We also use ground-based observatories such as our own Allen Telescope Array or the Very Large Array in New Mexico to search for signatures of technology among the stars. We undertake field expeditions around the globe. Those include Devon Island in the Canadian High Arctic, Lake Untersee in Antarctica, and programs in the Atacama Desert, the High Andes, and the Altiplano of Chile and beyond. So combined with laboratory research, extensive data analytics, including machine learning and AI, our science is both comprehensive and by design, very multidisciplinary. What makes us different than other organizations, and particularly than academic organizations in terms of how we interact between our sciences? It's interesting because from my perspective, I think humanity's approach to understanding nature is deconstructionist by design. We tend to break things down into component parts that we can digest and comprehend, and we organize our knowledge into disciplines like physics, chemistry, geology, and biology. But at the SETI Institute, it's really about putting the pieces back together and understanding the interdependence and interconnectedness of all natural phenomena. So it's ultimately about connecting the dots and realizing that true understanding happens at the intersection of disciplines, not solely within the disciplines themselves. So that's really one of our, what I call, unique value propositions at the Institute. So that's a very, very quick overview of the science we do. I want to talk very briefly about something we call the NASA Frontier Development Lab. And given that there's at least what I would consider to be above average capabilities at MIT in the areas of artificial intelligence and machine learning, I want to talk about this public-private partnership we have with NASA called the Frontier Development Lab. It's all about AI and ML for space science. The Frontier Development Lab was conceived at the Office of the Chief Technologist at NASA headquarters back in 2014, 2015, and it was set up to explore 3 underlying theses or questions. 1, what is the applicability of AI and machine learning to support NASA research priorities? And fundamentally, can AI and ML support basic research? Second was, can interdisciplinary teams of machine learning and AI experts combine together with their counterparts in in deep science domains work together in short time horizons and accomplish something of significance and importance. And third, is there an ability to engage public-private partnership to accelerate NASA objectives, doing things better, faster, cheaper, by embracing private industry and academia as partners rather than subcontractors to help advance NASA priorities. So it's all about power through partnership, and the program involves early career PhDs in AI ML paired off with early career PhDs in space research. We also use AI and deep learning and deep science subject matter experts and mentors to support the researchers. We engage, of course, NASA stakeholders, mostly within the Science Mission Directorate, but elsewhere within NASA as well. We have industry and academic partners. So it started as fundamentally a partnership between NASA and the SETI Institute. Google Cloud came along early on in the program and have been instrumental in providing massive compute resources, cloud-based compute and data storage resources, as well as algorithms and subject matter experts. So Google has really been transformative in enabling the FDL workshop and helping us do fast cycles and fast iterations in research, which enables the sprint to work. We also now have a sister program at the University of Oxford that in partnership with the European Space Agency that's been running for 3 years. And we're very excited about the growing geography and geographic impact of the FDL program. And here locally, the Frontier Development Lab involves lots of different partners, IBM, Intel, NVIDIA, Google, Lockheed Martin, Space Resources Luxembourg, Canadian Space Agency, US Geological Survey, and others. So it's really a large a partnership and collaborative ecosystem that makes the program possible. So if you'd like to learn more about Frontier Development Lab, especially if you're into AI and ML and are curious about its application to space science, you can check us out at frontierdevelopmentlab.org to learn more about that program. Lastly, I'm going to touch briefly upon our education and outreach. And this is really all about how we leverage the public's fascination with space science and exploration to design and deliver compelling and impactful education and outreach programs. So at the Institute, we have education programs that are built on the idea of taking advantage of the public's broad fascination with space exploration to teach compelling science that we think has both context and appeal. So our programs support teachers, they support undergraduates and young children alike, and they include the Airborne Astronomy Ambassadors Program, which is a NASA program for high school science teachers from underserved school districts, and it's 10 years in running. And you're going to hear later tonight from the head of that program at the Institute. We also have a program called Reaching for the Stars. It's about NASA space science for Girl Scouts. It's in partnership with the University of Arizona, the Astronomy Society of the Pacific, and others. And it's about bringing space science, STEM topics to Girl Scouts all across the country. And ultimately, it's all about making a difference. It's all about having impact. And in spite of our limited resources, our education programs are really exceedingly good at their reach and their impact. And the collaborations have really demonstrated some significant reach. The AAA program for teachers, for example, has over 200 alumni and has impacted more than 40,000 learners, reached over the past 9 years of the program. There's been demonstrated student gains in standards-based learning and improved attitudes towards STEM subjects, and importantly, also STEM careers and opportunities. We have over 185 undergraduate interns in our summer internship program, which is an NSF-funded program over the last 15 years. And more than 65,000 young Girl Scouts completed the badge program in the first year of that Reaching for the Stars program, and 100,000 girls completed the badge program in the second year. So it's really very exciting about what we can do, again, in partnership with others to have impact and promote science literacy and STEM. And we have new partnerships evolving with Cal Academy, with the Chabot Space Science Center and the Smithsonian Institute. You're going to hear about another compelling education program we have as well tonight that involves community college networks. So stay tuned for that. And lastly, outreach is equally important. And it's all about engaging the public to both inform and inspire. That's central to our mission as well. So here again, we take advantage of the public's fascination with all things space to promote not only interest in science, but also improvement in science literacy. By way of example, all these images that you see here have something in common that isn't obvious at first glance. It's actually nothing scientific. What they share in common is that they were all front page stories in the New York Times. So it really speaks to the fact that space is cool and it's fun, it's exciting. So why not leverage that to engage and enlighten? So that's what our outreach programs and education programs endeavor to do. So we have a large number of outreach programs that include Big Picture Science, which is a weekly science radio program and podcast carried by NPR affiliate stations across the country. We have a SETI Talks lecture series that's been running for more than 10 years with hundreds of amazing lectures. They include panel discussions and debates. All are available on our YouTube channel. And of course, presently we're doing the SETI Talk series using Zoom. And in fact, I think the next one is coming up on February 17th. We have an artist in residence program as well, where artists from all over the world work with our scientists for inspiration on amazing interpretations of their research, visual arts, performing arts, music, sculpture, and more. And it's all inspired by our science. And of course, we have a lively presence on the usual social media platforms and a website, SETI.org, where you can learn lots more about the Institute, our various programs, and how also to get involved if you're interested in doing so. And just a brief comment about the Artist in Residence program. One of our artists in residence is a gentleman named Felipe Perez Santiago. He's based in Mexico. He's a composer, and he's got a project called Earthling, which is about collecting songs and sounds from all over the world and sending them off into space. And he was just written up in The Economist in an article this week. So you can look for that as an exciting new way of space exploration and music interest. And I'll close just by saying that partnerships and collaborations are of central importance to our work. And they include government agencies such as NASA, NSF, and USGS, lots of academic partners, including MIT, University of Arizona, UC Berkeley, and other research institutions, including Planetary Science Institute, Cal Academy, Stanford Research International. We have corporate partners. I mentioned already Google, Lockheed, et cetera. So partners not only provide funding in some cases, but they also help extend the reach and enhance the impact for our programs. So that's a very quick thumbnail sketch of the SETI Institute. And with that, I'm going to turn it back over to Wendy, who will introduce our more interesting guests tonight, which are the actual science and education members of the SETI Institute, to tell you about their work. So let me stop sharing.
Thank you so much, Bill. It's great to get an overview of SETI, because I think a lot of times in the news we hear about, the search for extraterrestrial intelligence, but there's so many different components of that. I'm really excited to have a very, very esteemed panel of scientists and educators. And without further ado, I'd like to introduce our next speaker, who is Dr. Natalie Cabral, from who is the director of the Carl Sagan Center for Research at the SETI Institute. And she'll be talking about extreme environments on Earth and the search for biosignatures on Mars. So Natalie, over to you.
Thank you very much, Wendy. I am going to put this on presentation mode. So thank you very much. I am the director of the Carl Sagan Center, but when I'm not the chief scientist of the Institute, I am a planetary scientist and an astrobiologist, and I'm going to talk about that part today. So what I'm doing, I started as a Mars scientist, but I'm interested about the search for life and the characterization of habitability in the solar system and in the universe. And what I'm trying to do is to expand that beyond Mars. But right now there is a lot of focus on Mars. There has been a lot of focus on Mars for the past 20 years. So I'm going to talk a little bit about what I've been doing over the years here and what I'm doing now with the NAI team, which is the NASA Astrobiology Institute. The Institute itself now has become something else. It's morphing and evolving, but our team is still working on its project. So the baseline is that I am interested in studying habitability, what are a habitable environment in the solar system, and also trying to detect biosignature. So baseline, answering the question or addressing the question, where do you search for life? When was life there, and what type of life? We're talking about the origins and the nature of life and how we do that. So let me try to get to the next one here. Okay. And I do that in a number of different ways. So what we do, we start with the data from the missions. And in this case, this is the data from Mars. And we're trying to understand what the conditions were on the planet. And then we go to what we call analogs. And terrestrial analogs are those places that are not on Mars or anywhere else, but on Earth, but as close as possible to what the planetary environment we want to explore is. The reason being is that we want to understand how to explore and what kind of instrument we need to develop and what kind of resolution and what kind of spectral ranges we need to develop to figure out those biosignatures. So there are a number of ways of doing this. We can place instruments and payloads on board rovers. I have been deploying a number of robotic field expedition in the Atacama Desert. That includes Nomad, Marsicod, Hyperion, Zoe. But I also have been privileged to be part of the Mars exploration rover teams. And as part of that project, I was the spokesperson for the selection of the Gusev crater as the landing site for the Spirit rover on Mars. And we've been exploring Gusev for 10 years. And as you know, Opportunity for 15 years, although I was more with Gusev. But that being said, being part of that team helped me understand better what environment exists on Mars. And the next question, once you demonstrate that Mars is habitable, the next question is that, was Mars inhabited? So you go back to those terrestrial extreme environment. And the point with the exploration of those is that we don't have that many opportunities to go to Mars. We have a number of windows of opportunity where we can launch spacecrafts, but it's also expensive. So our best proxy is to do this exploration on Earth and learn on Earth. So we know, or most of all of us know what kind of condition we're on Mars, where you have a high UV radiation, very little water, etc. So we found places on Earth that are analogous to that. And we see how life develops, where it does, how it survives, what kind of strategy it uses. So that took me to bring my teams in very interesting places. Some of them are on top of 20,000-foot volcanoes, which have lakes on top of them. And the condition on top of those volcanoes are pretty close to what Mars was at the beginning of its history. So what we do there is that we dive into those lakes, and then we are sampling and trying to understand what are the signature of life and what we need to do to understand and identify this life. Or we can do that in a dry lakes environment as well, to search for fossil, biosignature, biomolecule, etc. So it's all about learning how to identify and detect life. First, recognize the environment and then learn how to identify it during a mission. And then more recently with the NAI project, we moved it to the next step. So for 20 years now, NASA and other space agencies have been really focusing on characterizing habitability. The next step is what Perseverance is going to do, and the Chinese rover is going to do within now 2 weeks, landing on Mars, which is the search for biosignatures. But how do you go from characterizing habitability to search for biosignature? They are not the same methods. You need to change the scale and you need to change the resolution. And so this is what we have been doing with the NAI team, which is to try and see if we can integrate the data that we have from the previous and current missions that are orbital data down to the ground, down to the lab, the scale of the lab. And so what you need to do is basically follow the microbial habitat. It's not following the water anymore, although it's related, obviously, but we have to understand the environment we explore at the scale that matters for microbes if we want to really look for life on Mars. And right now, the data we have is not suited for that. It's mostly orbital data with very local data by rovers. So our work has been to try and integrate data from orbit to the ground, to the lab, and then try if we can follow the microbe at those different scales. So we have been developing ways of detecting and following these microbial signatures. And in the way we are developing new exploration tools and methods that we can automate. And this is really a new thing. By that, I mean that exploring those extreme environment, we have realized that there are patterns in the distribution of extreme life on Earth. So there is a fractal nature of life, and it's repeating. Of course, it's fractal, so it's repeating at different scales, and we're trying to understand that, because when you have pattern, what is best than AI and ML to help you in your exploration. So this is one aspect of the current things that we are doing. And then I am very keen, and this is something that the Institute is also going to develop in the coming years. What we do for astrobiology is to study the coevolution of life and environment. So this is what you are doing. If you are looking for life beyond Earth, you are still studying a coevolution, because life doesn't happen in the vacuum. And I'm not making a joke here. It's not a pun, but really it's a coevolution. And the notion of coevolution of life and environment is directly relevant to what's happening on our planet. We also are a coevolution of life and environment. And what I'm trying to do is to also take the tools that we are developing for planetary science and space technology, such as the exploration of Mars, or in this case, and you can see here on this slide, a station that was actually studying remotely and autonomously a lake, a glacial lake in the Andes, as a simulation of a mission to Titan. But in the process of doing this, because Titan is so far away, we don't have the same communication than we used to have, even with Mars. So we have to develop more autonomy, and we need to make those robots really real team members. They have to be autonomous. They have to be able to make decisions, understand the priority of their mission and what is important for the mission, etc. So we develop a number of autonomous detection algorithm, and those were all related to environment, how to detect storm, how to detect changes in the water column, etc. When taken all together, these algorithms can work as well to detect changes on Titan as they can detect changes on our own planet. So this is how it all comes back to Earth, where we are actually applying what we develop for planetary science and space technology to the monitoring and forecasting of climate change. And in the coming years, we are going to use what I presented with the earlier slide, this integration of orbital data to the ground as well for the forecasting and modeling of climate change. So I will stop here for now, but in a nutshell, this is what we are doing right now with the NAI team and with a few other projects here at the SETI Institute.
Thank you so much, Dr. Cabral. This is all really exciting. And one of the things that I absolutely loved about the SETI Institute is that, there's a lot of learning going on, a lot of research, like what Dr. Cabral is talking about. There's also a lot of giving back and that passion for spreading that learning. So I want to welcome Dr. Simon Steele, who is the Director of Education, Outreach, and Communications at the SETI Institute, to talk about a NASA Community College Network that SETI is working on.
Great, had to find the unmute button there. Wonderful, thank you very much. It's great to join everybody. I'm not from Boston, but I know the city very well. I studied just a bit around 128 out at Brandeis, so I'm reasonably used to cold weather, but now I'm enjoying the slightly more temperate climate of California. All of these exciting things that Natalie is talking about, and we hear more about exciting discoveries in a little bit, are things that the education and outreach team want to share with everybody. And in fact, NASA have that same philosophy. And last year put out a call for proposals to help NASA science and NASA scientists reach underserved and underrepresented communities across the US. One of those communities that we felt was very, very important and have not been reached are those students in community colleges. And so we put a proposal in from the SETI Institute that was accepted. The proposal, the project started on January 1st this year. So it's a brand new proposal, brand new project, 5 years long. And the SETI Institute now is tasked with working with all of NASA science to bring the amazing discoveries and the amazing science of NASA into the nation's community colleges. So the question is, why community colleges as a target for NASA science? And the next slide will give a little bit of a demographic as to why this is an audience that really needs attention. Just if you look on the left-hand side, just a few basic statistics. Of roughly 300,000 students who take introductory astronomy every year, an estimated 35 to 43% of them, so that's almost 50% of students in the United States take their introductory astronomy courses in community colleges rather than four-year colleges like Harvard and MIT and so on. A lot of these students taking intro astronomy courses are not necessarily going on to become scientists. Some of them will still be trying to decide where they want to study and what they want to study. But most of these students, this will be their last exposure to a science course. So not only is there a responsibility in these science courses to teach them and to help them, get as much out of the excitement of NASA science and NASA exploration as possible, but also to bring across the concept of the methodology of science, because these students will go out to become citizens, and we would like as many citizens as possible to be able to look at a newspaper, look at the headlines, and be able to decipher, if you like, what is real science and what is fake science. A very, very important skill. 1,000 US public accredited degree granting two-year institutions in the US, so 1,000 colleges potentially we could reach, over 700 teachers courses in astronomy and space science. And I use the term astronomy broadly just for simplicity here. We're talking about anything that NASA, the NASA Science Mission Directorate, as it's called, teaches or rather sort of works on. That includes earth science, it includes heliophysics, it includes astrobiology. These courses are taught under, as I said, astronomy, astrobiology, physics, geology, by more than 1,300 instructors across the US. A significant number of these are part-timers or adjuncts. That means they are not tenured. They may be teaching at 2 or 3 different colleges. They may have teaching loads equivalent to high school teachers. And they really have not got the time to keep up, if you like, with the latest discoveries and latest techniques in space science and education. And in a survey of these instructors showed only 23% actually had degrees in astronomy and astrophysics. So we would like to help the teachers who have backgrounds in earth science to develop their skills and their backgrounds in astronomy, and likewise, if they are astronomers, help them in their backgrounds in astrobiology and so on. And the table, the fast facts table on the right-hand side, this is from the American Association of Community Colleges. I won't go into too many of these totals, but if you could see the bottom left here, significant demographics of community college students, 29% first generation to attend college, 15% single parents, non-citizens, veterans. The gender breakdown, 57% women. This is an audience that generally does not get all of the resources and does not have the resources that four-year colleges do. So what are we actually going to do with this NASA Community College Network? We have 3 main goals. The first one, top left, illustrated nicely by the antennae galaxy, Hubble image of 2 interacting galaxies, which is just beautiful. We want to broker direct partnerships between NASA, the NASA subject matter experts, and community college instructors themselves. We'd like to set up sort of bespoke mentorship programs where we can get scientists involved in helping instructors reach the latest results, the latest data sets, and whether they want to go into the classroom or whether they want to provide materials, we want to make this process happen. Top right, a nice picture of Perseverance rover, but in order to enhance the teaching capabilities of these instructors, we want to provide a set of highly quality, curated, audience-appropriate materials. So it's all very well NASA producing a beautiful image or a data set of an exoplanet transit, but we need these in the format that are readily available and audience-appropriate for the instructors and their students. And the last panel, bottom right, is to provide professional development and training, not only for the instructors. As I said, they may be biologists teaching astronomy courses. They may be astronomers struggling and wanting to teach astrobiology in their courses, to help them with interpreting the latest results and the latest data coming from NASA, the latest discoveries, to make it suitable so they can then continue that on to their students, but also providing professional development for the scientists as well. A lot of scientists, and we're going to hear from a few in a minute, Margaret and Dana, who are scientists who are naturals at going into a classroom and interpreting the complexity of scientific discovery for students. But a lot of scientists may be not comfortable doing that, and we would like to help those scientists make that transition and have outreach and education an integral part of their profession as they move forward in science. So that is a very, very quick overview of our new program at the SETI Institute. Bottom left is the website address if you want to take a quick peek, www.seti.org/nccn, and I'd be happy to answer any questions now or in future about this and any other project we have at the Institute. Thank you.
Thank you, Simon. And that set us perfectly for our next talk, which is by Dr. Margaret Race, who you talked about. But before I introduce Dr. Margaret Race, I wanted to just quickly note that there's already a very active Q&A going on in the chat. So for those of you who are not aware, we are going to be doing Q&A at the very end. I know that you have lots of questions, but please hold them until the very end. And in the meantime, if you do have questions you really want to ask, please feel free to put them in the chat, and I'll be collecting them as well. And I know some of our speakers are answering them directly, which is wonderful. So next, I would like to introduce Dr. Margaret Race, who is the Senior Research Scientist at the Planetary Protection and Risk Communication at the SETI Institute. So over to you, Dr. Race.
Okay, thanks a lot. Well, as you said, that we are approaching the arrival of the Mars 2020 mission, which you can see on the left, the rover, and then the samples that are there. And so I thought I would talk about some of the work I've done that has to do with anticipating Mars sample return, which won't be until 2030. But for 3 decades, SETI Institute and its assorted researchers have played roles in Mars sample return planning and research. I was somebody who grew up in Boston, and after I graduated from University of Pennsylvania, came out to the West Coast. I was doing work on kind of science and technology and the policy implications of it. How do you think about making decisions based on science that you learn in a variety of different things? I was teaching at Stanford and then went on to the University of California, where I worked with the Office of the President. And while I was there in the Division of Ag and Natural Resources, I was picking up information about all sorts of mixes of things, from the environmental impacts of pesticides to forest and fire management to water pollution, which I was really quite versed in. I'm actually a marine biologist and ecologist by training. So I got this phone call from SETI Institute one day asking if I would come, from NASA Ames, asking if I would come to a workshop on biosafety and containment. This was in 1990. And it turns out while I was at Berkeley in Office of the President, we had lived through the nightmare of the first outdoor release of a genetically engineered organism. Steve Lindau, who was a professor at the Berkeley campus, was proposing and had gotten approval for the first outdoor release of a genetically engineered microbe. It would be a microbe that would put bacteria on potatoes, believe it or not. And it turns out that those would be able to live in much colder conditions, fully 5 degrees lower by having these bacteria on them instead of the normal bacteria. It was no big deal. It didn't change anything about the potatoes. But it turns out there were people who are very upset about genetically modified organisms. And the Asilomar Conference in 1975 had said, we will keep genetically engineered organisms in biocontainment facilities and not put them outside. So this was the first outdoor release. The hue and cry from the public was quite amazing. California has environmental impact statement rules, and so does the federal government. And what happened is that Lindau's experiment for the outdoor release, a test at an agricultural field station, which was approved for 1983, was delayed fully 4 years. And when NASA called, when Ames called, they were saying, would something like that cause a problem for a sample return from Mars, which at that time was being considered for about 2003 launch and a return around 2007, 2008. So that got me into work on looking at what does it take to go through an environmental impact statement process for a return sample that probably doesn't have life in it, but might. And it's a life form that we don't know what would be in it. So here is an example similar to a new technology, bringing something back, and where are you going to put it? Would the analogs, the biocontainment labs that we have on Earth, be an appropriate place to bring back samples? Who would go through an environmental impact statement process to have one of those near their home? And how long would all of that take? So I quickly became familiar not with just the US environmental laws, but the United Nations Outer Space Treaty of 1967, which is an international consensus treaty that only has 2 counterparts. One is the Antarctic Treaty, which sets aside Antarctica for research, science research. And the other is the Law of the Sea, which you can understand has a tremendous amount of deliberation and science and controversy. There are well over 100 signatories, national signatories of the Space Treaty, and it's for the peaceful exploration and use for the benefit of humankind. Article 9 of the treaty holds that you must avoid harmful cross-contamination of planets and satellites and any adverse effects on Earth from space exploration. So in looking ahead, also it applies not just to government agencies or entities, it applies also to commercial and private parties. So in terms of practical implications, that means that anytime you're going to launch something, you have to think about forward contamination. What are you launching with your spacecraft? Because you need to avoid the introduction of terrestrial microbes on outbound spacecraft or equipment. Backwards contamination, you avoid the introduction back to Earth of biological contamination or life forms in returned materials. Now, at that time, that wasn't a big deal because we really weren't planning right away to send anything, but we had to consider, what does this mean and what does it mean for the mission, the equipment? There were no people going, this was robotic. And planetary protection as a general thing actually looks at categories. They depend upon where you're going. If you're going to the moon versus a location like Mercury or Venus that are uninhabitable by and large, you have fewer restrictions than if you go into a place like Mars. So your category and stringency of planetary protection depends on the target location you're going to and the activities you will do. So whenever you're proposing to go someplace, you have to make sure that you've told NASA or other countries what it is you're going to do and where you're going to go. Likewise, you have to think about how you're going to put things together and assemble your spacecraft and do all the work there. And you have to think about what other impacts might be occurring. Next slide, let's see. Okay, so if you think back, so that it was a treaty from 1967. It actually began out of discussions with the Russians and the US in '59, around the time that Sputnik went up. And the highest priority is for planetary protection is to make sure you don't, make sure you don't bring back any contamination, don't take anything up there, and you're careful about what you do. So forward contamination in 1963 was the real concern, because you didn't want to introduce anything that you brought on your spacecraft that would interfere with determination of whether there might be life someplace else. You didn't want to jeopardize scientific experiments. So planetary protection policies and requirements definitely adapt over time, much like all sorts of other regulatory things that we have. And we don't have a lot of data. So we're gathering the data and trying to say, how does it fit in? So at the time that Viking mission went, there's a picture on the right there that shows the Viking spacecraft's material in an oven, literally a room-size oven, and it was heated in the oven to sterilize it for the outbound spacecraft. A lot of things we have now can't take sterilization in the form of heat like that, or and individual pieces of equipment and instrumentation might need much gentler or specific kind of cleaning. So if you looked at the first approach, took a lot of the national studies, so quarantine protocols, how do you develop a protocol? What are the issues for sample return mission? And then there were multiple National Academy studies looking at biological contamination, what would happen if we put materials on Mars, what are the issues and what do we recommend about when you bring them back, and how do you evaluate looking at biological potential from samples returned from the bodies. If you only drill rocks, you don't get the same data or information that you would from bringing back regolith from a sample, or dust, for instance. And so there's lots of information to think about what would go into planetary protection planning. The next era of planetary protection.
Margaret, sorry,
Yes?
I was just watching the time a little bit. If we can wrap up in the next few minutes, or 2 minutes, that would be great.
Mm-hmm. So the next era had a focus really around the astrobiology, which was a focus for searching for life. And there was another whole series that was talking about going to Mars. And now in this past decade, we've been looking much more at sending people to Mars. Well, people are walking containment for microbes of all sorts. So when we send humans up there, we know that there will be problems because they'll bring the microbes with them. Here is an example of the kind of things that are done to implement planetary protection, is bioburden reduction of the hardware from different methods, recontamination prevention. You see things that are all rebagged and things. Bioburden control during the assembly, test, and launch operations. Someone is down there actually taking samples and verifying with assays what load of biological materials are on it. And at the end of a mission, there's a burn up and breakup analysis. Make sure you don't crash into Mars, maybe send it off into the sun, and documentation of everything. This picture in the middle here is the Perseverance. They did extreme cleaning on the sampling tubes because those will come back. And so they had the most stringent of cleaning that was done in clean rooms before these will go up into Mars. Next one. The only time we've actually put together a draft protocol on what to do with the canister when it comes back was back in the early 2000s. And they were looking at what kind of physical chemical testing, what kind of life detection, and what kind of biohazard analysis would be done. And environmental health and monitoring was very important, with criteria for release to be determined, and how do you get the public to interact with you. And that's a very important part of any kind of NASA mission. So even though Mars sample return is anticipated for now 2030, there's still a lot of other issues, not just science ones. There still is no biocontainment lab or plans, which if you go through an environmental impact statement process for the state or the federal, it could take up to 10 years to do it. Currently is a debate over the level of sterilization. If you sterilize things before you bring them back, it's less worry about having an impact like pandemic of sort. Where are you going to sample your and do your testing? All of those things, if you use full sterilization, you reduce the containment needs, but you also reduce your science options. if the public is concerned about.
Margaret, you're going to have to wrap it up here because I mean, there's a lot of material you're covering here, and it's very
Okay.
interesting but
Yeah.
detailed. So
Great.
people can get into this detail perhaps afterwards.
Okay, and I did this so that people want the slides, they can have them, but this is a lot like COVID or CRISPR or synthetic biology. There is no decision-making policy or process right now for the discovery of extraterrestrial life. And there's a whole group of folks that are looking at ethics and religion, philosophical aspects, and implications of dealing with the environments up there. So who makes the decisions? Right now, it's the science and the governments. So we have an Achilles heel of back contamination and potential accidents, and a lot of lack of information about what the benefits are for people. So it's a stepwise process that we go forward. We're thinking more about science and technology, but we have to involve the risks. Think about the legal aspects of it, the policy coordination, and the analogs that we can use for criteria, including COVID, for example. And it's a lot more than just science. So you're using the exploration and thinking about exploitation in the future and preparing dialogue that will include not just science, but also commercial and private users. And you got to think about the time horizon. So sorry, I went over a bit, but it's very, very complicated. And anytime you go through government, you can see that.
No,
Thanks.
totally. Thank you so much. And I always wish we had more time for the lightning talks. It's all so interesting. But the great news for everyone here is that I believe all of our scientists and educators' emails are publicly available on the SETI website. So please feel free to reach out if you have more questions. We can't get to them, but you know, as you can see, we have a very passionate panel who would be more than happy to talk to you more about their areas of expertise. Next, I would like to invite Dr. Dana Bachman, who is the NASA Airborne Astronomy Ambassadors Project Principal Investigator, to give the talk. And I will be presenting my screen because Dr. Bachman will not be able to present his screen, as you can imagine. So let's
Margaret,
see.
you need to stop share if you can. There you go.
All right. And can everyone see my screen? Perfect. Over to you, Dr. Bachman.
You have to unmute, Dana.
Thank you for presenting my slides, Wendy. The reason I can't do it is an embarrassingly simple technical problem. But anyway, onwards. This is a program, an education program to which Bill Diamond referred briefly in his introductory remarks. It's a professional development program for teachers that aims to impact student learning and STEM engagement in districts across the country. And we use as our primary platform NASA's Stratospheric Observatory for Infrared Astronomy, pictured in a test flight over the Sierra Nevada here with it's a 747 that NASA bought, used from United Airlines, and then altered, modified to carry a 2.7 meter telescope behind a rollback door on the port side here. And you see on the tail the NASA logo, but also the DLR, the German space agency. It's an 80% NASA, 20% German project. And you see in the middle picture a group of AAA teachers plus their flight escort Pamela Harmon at our dedicated console on board Sophia during a science flight. Sophia is an astrophysical observatory, astronomical observatory that's used by astronomers all over the world, but particularly American and German astronomers. And then in the bottom picture is the NASA IRTF 3-meter telescope on Mauna Kea. That's our backup site for the teacher STEM immersion experience at times when Sophia isn't available. So next slide, Wendy. Thank you. So I'll try not to read all of my bullets, but here you see on the left, you see a group of teachers at our console on SOFIA, and we bring the teachers to Palmdale, where SOFIA is based, Palmdale, California, NASA Armstrong, for a week, where they're talking to NASA engineers and scientists and other technical staff about their jobs, and then fly twice on SOFIA, all-night research flights of SOFIA. The teachers are selected by a peer review panel. And as Bill noted, we've had so far 200 teachers since the program was inaugurated in 2011, about 25 to 30 teachers each year. And my colleagues Coral Clark, Pamela Harmon, and I take turns escorting the groups of teachers, 4 to 6 teachers at a time, on these SOFIA flights. And this is decidedly not a joyride. They're responsible for understanding what the scientists are doing, how they've designed their experiments, how they're changing course in midstream sometimes. Often, actually, the real as science is really done, you don't end up doing it the way you thought you were going to do it. But the teachers are not going to take back frontier astrophysics necessarily to their classrooms, but instead the process of science, how scientists do their research. And on board the SOFIA on a flight, there might be anywhere from 2 to half a dozen scientists, but there's a large crew of telescope operators, mission directors, and flight planners, and IT data reduction people, and also the pilots, of course, up in the deck. Okay, if we go back. So what we do, the flight facilitators, we take the teachers around to make sure that they've talked to everyone on board about how they got where they are, what they're doing, and their career trajectories, so that they can take that back to their classrooms. And the teachers, although they sort of knew it theoretically, they are always struck by how much teamwork is involved in getting a group of about 20 people, that's a normal crew on a SOFIA flight, to do this complicated dance of getting the telescope to point on a flying platform, to point at astrophysical target, and take data and store the data and analyze the data. You see in the middle picture that's our console for the teachers. It was designed in from the time that SOFIA was conceived back in the mid 90s. This is a view facing aft towards the telescope chamber. This is shirt sleeve environment and the main deck, and the telescope is behind a pressure bulkhead. But the scientific instrument, camera, or spectrograph is accessible from the cabin by the scientists if they need to make adjustments. So the console behind, farther aft, that you can see in sort of the middle distance, that's where the scientists are sitting doing their work. And then after flights, then the teachers go back to their classrooms wearing the nifty NASA flight jackets that we give them and their hometown heroes, and then take what they've learned and implement it in their classrooms. To this point, they've been high school teachers, but we're happy to say we just selected the 2021 cohort of teachers, and this time includes community college and middle school teachers in addition to high school teachers. So, at the bottom bullet here, as mentions West Ed, which is a education evaluation organization. They conducted a controlled experiment in the 2017 to 2018 school year with a total of 2,000 students of 38 teachers. There was a treatment group, they so-called, and a control group. And the impact on the student learning of the electromagnetic spectrum and astronomy content material is a 9 standard error difference between the treatment group and the control group, because the teachers had the SOFIA experience and the learning, the content learning that went along with that. So next slide. So there's a little bit about
Dana, if we can just wrap up in the next
okay,
minute, that'd be great. Thank
this
you.
is a little bit about Sophia, but it's in the stratosphere above the water vapor. Most 99 or more percent of the Earth's water vapor that screens out infrared radiation in particular. And I think we can skip to the last slide then. And I guess you're going to provide all the slides, but here's the SETI Institute's website, Sophia's Science Center's website, and the NASA IRTF's website. So that's it.
Yes, I will share this slide, make the slides available to all of the attendees. Next, we thank you very much. Next, we have Dr. Carol Cleland, who is the professor of the Department of Philosophy and director of the Center of Study of Origins at the University of Colorado. And she's a SETI Institute affiliate. So Dr. Cleland, over to you.
Thank you. So I apologize for not having slides because I was told these talks would be 5 to 6 minutes and I didn't think I could work slides into them. So I'm going to talk and you're going to have to look at my ugly mug while I do this conversation. So I want to talk as a philosopher of science because I'm a philosopher of science and I publish in both science journals and philosophy journals. So I work with scientists as well as philosophers and I publish in both kinds of journals. And I'm going to talk about my work that's pertinent to the SETI Institute and pertinent to the search for extraterrestrial life. And I would argue could be extended to the search for extraterrestrial intelligence. So many scientists, many people, and scientists included, believe that a definition of life is required for searching for extraterrestrial life. After all, how are you going to recognize unfamiliar forms of life unless you have a definition to tell you that what you're looking for? And it turns out there are two serious problems with this approach. One is more scientific and the other is more philosophical, having to do with the nature of definitions. Both of them are grounded in logic. So I'm going to start with the first one and explain them, and then explain the solution that I propose both in my book and in the literature, the philosophical and scientific literature, for overcoming this dilemma that the definitional approach for searching for extraterrestrial life, which everybody still loves, is still very popular, really ought to be abandoned. So the first problem is our experience with life is limited to a single example. And even worse, we have reasons for believing that that single example may be unrepresentative of life, positive reasons. And it's not just we have a single example, so it might be unrepresentative of life, but we have positive reasons for thinking that might be unrepresentative life. So let me start by just pointing out that biologists, and so I'm going to give a very quick overview of what these reasons are. Biologists have shown us that all life on Earth is descended from a single, all familiar, all known life on Earth is descended from a single example of life. And this a single example of life is a last universal common ancestor, affectionately known as Luca. And moreover, biochemists have shown us that life on Earth could be at least modestly different in its molecular building blocks. It could have used a different suite of amino acids to build its proteins. Protein chemists have shown that they can build non-standard proteins out of non-standard amino acids, amino acids that aren't in those 20 amino acids that are used to build familiar life, and they would be functional in the right organismal environments, except there aren't any on Earth. And similarly, nucleic acids. We know Steve Benner and others have shown that different nucleobases could be used to store hereditary information. We know that we could have had a different genetic code and a different coding schema. Maybe not a triplet coding schema, maybe a duplex or a higher order coding schema. So we know, both biologists and microbiologists shown us that life could have been at least modestly different. We're dealing with a single example, and we don't know how different it could be. And so this is a central problem because how can you generalize from a single example, this is a logical problem, to a phenomena in general? Because you don't know what features of the single example that are universal to the single example are basically particular to that particular case versus particular to life in general. You just can't tell that from a single example. Let me give you an illustration to kind of bring this out. Consider an alien who wanted to generalize about mammals based on a single example. Let's pick zebras. It's very unlikely that our alien biologist would pick on the mammary glands because only half the zebras have them. More likely, what do all zebras have? What's universal to zebras? Their stripes. But any biologist will tell you that would be a mistake, that the mammary glands that are had by zebras is more essential to their being mammals, more fundamental to their being mammals, than their stripes, which are accidental. They're not accidental in the sense that they have adaptive advantages in the right environment, but from the point of view of mammals considered generally, they're not important. And that's the poor problem we have. How many of the features that are universal to Earth life are actually features that are due to chemical and physical conditions that on the early Earth when life emerged? How do we discriminate the fundamental from the non-fundamental? So that's the scientific problem. That's also a logical problem, but there's a deeper problem. It's philosophical and also logical, which has to do with the nature of definitions. Definitions provide analyses of concepts that we have. If you analyze, if you want to give a definition of bachelor, you sit there and you think about, well, what's my concept of bachelor? Unmarried human male. And if somebody says, oh no, bachelors are married, then you say, you don't understand what the word bachelor means. This person's not going to be able to convince you that bachelors are married without changing the meaning in the English language of the word bachelor. Now consider, as an example from natural science, somebody who is in the 17th century wonders what water is and proposes a definition of water. If they propose a definition of water, and they are going to analyze their concept of water, they're not going to come up with anything like H2O. Why? Because we don't have molecular theory yet. We don't even have the periodic table. Without that theoretical framework, nobody is going to discover through analysis of the concept in the 17th century of water, that water is H2O. They're going to come up with something like liquid, transparent, thirst quenching, etc. So the point I'm trying to make here is that we have two big problems. One is generalizing from a single example that we have reason to believe is unrepresentative. And the other is the very nature of definitions, which is that they only tell us what we already know. They only analyze the concepts in our head. And a biologist, an astrobiologist, doesn't want to know what our current concept of life is. He or she wants to know what life really is, whether it's on Earth or on Mars or on a planet circling Alpha Centauri. So that's the central problem with the definitional approach. So this looks like a dilemma. How can we search for unfamiliar forms of life if we can't define life? How are we going to recognize something that's different from our form of life if we don't have a definition of life? Well, I've proposed in my book, The Quest for a Universal Theory of Life, where I talk about all these issues about definitions, and in an astrobiology article, which was published the June before last, a different strategy. And here's the strategy I propose. Instead of using defining criteria to search for something that's going to qualify as life, we search for potentially biological anomalies using tentative, not defining criteria. What do I mean by potentially biological anomalies? I mean phenomena that are provocatively lifelike. They have certain characteristics of life that make you think that, gee, these are good candidates for life, but they also have characteristics that are unanticipated, that you would think would not be characteristic of life, and you would think they'd be characteristics of non-life. But the definition, because of the latter, they're going to be classified as non-living, even though they have these characteristics that are kind of lifelike. So the basic idea here is that instead of an up or down decision that we found life or not life, which is what NASA would prefer, I think it's very naive to prefer that if you're looking for really unfamiliar forms of life. What we do is we look for something that shouldn't be there, that is difficult to explain, either with our current understanding of biology and also with our understanding of what is an abiological process. And so the basic
Carol, sorry to
oh, I did it.
If we can
see,
just
okay. Now I'm actually at the very end. And the very end is that if you search for potentially biological anomalies using tentative criteria, what you're going to do is you're going to try to find cases, phenomena that are worthy of further scientific exploration for life. It's not going to be a thumbs up or thumb down. It's going to be, we're going to go out there and, oh, let's focus on these because these are truly interesting, potentially biological cases. And I think in general, by the way, that I have a book, another book I'm working on the role of anomalies in scientific discovery. I think the role of anomalies in scientific discovery, if you look at the history of science, is really, really important. So even without, I thought I would be much quicker, sorry.
No, thank you so much, Dr. Cleland. That's very, very interesting constructs to think about, because I often wonder what exactly is life. So thank you for that very enlightening talk. Next, we have Dr. Pamela Suk, who is a planetary scientist and asteroid research affiliated scientist at the SETI Institute. So Dr. Pamela Suk, next over to you.
Hello. Well, first, thank you everyone to be here and listen to us. My name, like Wendy says, Pamela Such. I work in asteroid research, space resources and planetary defense. I'm like geologist, I like to talk. I was told to keep the talk short to 5-6 minutes, but I managed to reach 8 minutes. So I hope everyone has the patience to be here. So how we define space resources? Space resources is like on Earth, every natural resource that we can identify, we can determine, we can calculate the reserves, and we can exploit or take in order to produce any material that human needs to survive. Is this concept new? No, it isn't new. It was actually developed more than 100 years ago by a Russian scientist, Tchaikovsky, that was talking about the evolution of human being and talking about that, like a baby in a crater, the human will actually at some point explore the solar system and conquer the solar system. And in that order, we need space resources to be studied, understand, and investigated. What exactly are space resources? Like I have defined before, is every material that can be identified, explored for the human beings in order to achieve the necessities. But basically what we are looking in our solar system is water and hydrogen and oxygen in order for the human being to be able to habitate the moon and Mars, and in the future, the deep solar system in order to survive. These are images of recently discoveries of water in our solar system. This is the images from the moon in the South Pole. You know, there is a mission going soon, the Artemis mission. For the Artemis mission, they are looking for resources so the humans can actually have an habitat and survive there in a long period of time. So Sophia has discovered water in the moon. The water is ice water. In the Itokawa asteroid, sorry, I have my son arriving. In the Itokawa asteroid, the Hayabusa mission has actually also discovered ice water. In a NIA, it's a NIA asteroid mission, deep in space, like the mission Juno and Cassini, has discovered water in the moons of Europe and Enceladus in the system of Jupiter and Saturn. And recently, NASA, well, a few years ago, NASA has shown evidence that water can be still active and existent in the surface of Mars. And in that order, the new rover, Perseverance rover of NASA, is going to search for water on the surface of Mars. Like I mentioned, the space resources are very important in the order to prolong life in space for humankind. And in that order, ESA has presented a strategy plan where they actually prove that in short terms in the moon, water can be exploited and can be used for human consumption. In long term, metals can be acquired from regolith from the moon in order to build using 3D printers. They are going to extract the metallic content and build habitats. And from asteroids and Mars is a long term, it's in between 20 years and more, 40 years to extract these metals and water. But actually the applications for these space resources will be rocket fueling, life support, infrastructure, equipment, and bringing back resources to Earth in the future when needed. If we go what we know about space resources today and what is being talked about the space resources today, well, the Congress of the United States in 2015 has approved a law that says that the first to get to an asteroid or to any other resource in the solar system can exploit it. And the Luxembourg country in Europe in 2016 has done something similar in that order. What they have do with these laws is to make the private industry join the space agencies and the research for the development of the technology and the methodology needed for the exploration and the exploitation of the space resources. The first one talk about actually numbers and how much the cost of this can be. It was actually the MIT in 2012 or 2014, if I don't remember wrong. They actually say that going to space, explore, find, and exploit a resource, for example, the moon or a near asteroid, is similar cost of the exploration and the exploitation and the put in production of a mine on Earth. So, and the similar amount of time as well, from 20 to 25 years. That is what actually it took us to find, to discover, to find, to extract and produce mineral from a mine on our planet. But welcome back, welcome to Space Resources, how we actually are studying there here on Earth. So we have in-ground research, we use laboratories, for example, where we study meteorite samples to understand the compositions, to understand what is important in those samples that we can actually extract in the future. We study asteroid simulations also. We use vacuum chambers like this one in here. So we simulate the moon surface, so we simulate the asteroid surface to study them. We also use simulate samples from Enceladus and Europe to understand how we can extract water and liquid water or gas from these surfaces. And also there is some missions, they're called going to Earth, Earth analogs of Mars or the moon or some asteroid surfaces. So simulated missions where we test instruments on place, like the Amadi mission. I have participated in the FAR area. In situ technology for space resource exploration and exploitation. Well, some private companies like Planetary Resources has present instrumentation identification for water in NEAS asteroid. Water is the most important. iSpace recently with her base in Luxembourg and in Japan has achieved the payload of a robot that is going to explore for resources in the surface of the moon in the South Pole with during the Artemis missions. And of course, now
hey,
in
Pamela,
February,
sorry, just if you can please wrap up. Thank you.
Sorry, the Perseverance rovers is going to land in Mars, and they have an instrument called MOXIE that is going to be the first actually production instrument of oxygen, like a real from CO2, like a real production of space resources in space for the first time before the moon. But just to close, how is this important if we want to understand why we want to go out, why we want to look for resources, and how can this actually be related to the search for life or intelligent alien life outside of our solar system? We, like, this is very philosophical, we, like human beings, since the start of our very evolution, we have been moving, and moving means evolution. We have been moving, like you see in these images, from Africa to every other continent on our planet. And like the Polynesians, they have achieved these amazing travels in the Pacific Ocean to this little island with non-unparalleled, very small resources that they can actually find on their travel, like the water from the rain or others. When human was evolving, eras are named in the resources that were being used to achieve the human evolution. So if we take all these concepts and we see where we are going to the solar system, all these missions, I love to use this image, all these missions that they have already achieved the solar system exploration, and the future missions that we're going to use to go to conquer other places in our solar system, we need those resources also to survive, like our past, the past humankind has used them during their traveling and conquering our planet. But how we can use these concepts that we know, and we know very well, to search for intelligent life outside of our solar system. We have space telescopes that they are pointing out, they're looking for outer planets, and they are studying the outer planet composition. They are finding those planets in habitable zones, and they are looking for water, CO2, or methane that we know they are components for early life. So if we see the TRAPPIST solar concept over here, and we see that they have some rocky planets, they have water, and they have ice water like we have in our solar system, and we can find molecules that they are from the beginning of life, we can understand that actually in that system, life can evolve as well, like to intelligent life like we have evolved here. And in that order, we can also understand that aliens like us need to use resources in order to evolve and in order to create advanced civilizations. Oumuamua was an asteroid that was discovered a few years ago, and there was a scientist from Harvard that was mentioned that can be an alien material that was just flying by our solar system. Well, if we understand that, like, it actually can be happening, can be real, in order to have that material flying by, those aliens has the need to explore and to exploit the space resources around them. So sorry, I did it too long, but
no, thank you.
If anyone has
really,
questions, I can.
Yes, really appreciate your presentation, Dr. Soch. Next, we have James Boyd, who is a researcher in econometrics, AI, ML, data and policy, and technology strategy at the New School in Boulder and a SETI Institute affiliate. And after James, we'll have one more scientist who wasn't listed, but she will be talking about astrobiology after. So please stay on with us. I know we're getting to 6:30, but for those of you who can, please stay on with us because we do have an amazing two presentations to conclude. Over to you, James. You might be on mute.
My apologies. All right. Hello, everyone. I'm going to speak about hypotheses generation in SETI, which is somewhat of a complement to the lecture given by Professor Cleland, but I take my own kind of respective approach. So why do hypotheses matter in SETI? Well, in SETI, in the end, it's the search for extraterrestrial intelligence. So we're conducting some sort of a search. We have some sort of an idea of what we're looking for, though that can vary depending on your hypothesis. And in the end, you're trying to conduct some sort of a search informed by your hypothesis, and your findings should either confirm or disconfirm, strengthen, corroborate, or challenge your hypothesis. If you have a concise hypothesis as well, it can make your study more reproducible, so it can be a shared undertaking by a greater scientific community. So in my opinion, because SETI is still somewhat of a rather immense challenge, it very much helps to have a very good hypothesis that's well defined so that you know exactly how you defined extraterrestrial intelligence and what you're looking for. So I'll review a couple of kind of classical or canonical classes of SETI hypotheses. So some hypotheses address what's called abiogenesis, or how does life originate? So there are primordial soup hypotheses, which you might have heard of, that biochemists might want to talk to you about. There are more exotic hypotheses such as panspermia, which hypothesizes that life might actually be disseminated by one common ancestor throughout the cosmos. So there are different approaches to abiogenesis, but it's a particular class of explanations for the origins of life, really at any kind of scale, microbial to something that has the kind of intelligence that might be human comparable. There are also hypotheses that address the Fermi paradox, which is somewhat meta-methodological. We've been conducting SETI for some time. We haven't found concrete traces of highly advanced extraterrestrial intelligence. And so we might ask why. Why is it that we don't observe it in abundance, given the number of planets there are, the number of galaxies there are, and the amount of time that has elapsed that would permit an advanced species to conduct and develop highly advanced technologies. And there are different kinds of hypotheses that address this, such as the rare earth hypothesis, which states, okay, yes, we're able to enjoy habitable conditions on Earth. That's why we're able to sit here and ask questions, but that's actually a rather rare terrestrial affordance that might not be as common as we think. There's also the great filter hypothesis, which states that there are a number of incremental and compounding challenges that prevent the origin of intelligence, or what's called noogenesis, from small microbial life. So at every rung of this kind of a ladder of this filter, it becomes more and more difficult. And that's why intelligence gets kind of filtered out from the cosmic landscape. And there are other more exotic hypotheses that concern whether or not advanced technologies would even be detectable and how we would really kind of look for them. Finally, there's the anthropic principle, which asks, well, how did human intelligence arise in the cosmos? What kind of cosmic conditions permitted not only the development of the solar system, but the development of Earth within the solar system? And if there are certain kinds of cosmic conditions that have made it possible for anthropic intelligence to arise, and if we're a rather privileged species that have benefited from those conditions, do those engender biases or selection effects that might distort or in some way shape our own search? So those are some kind of typical classes of SETI hypotheses, but I still think that there are many more kinds of hypotheses that we can consider. So for me, when considering the search for extraterrestrial intelligence, I really want to ask the question, well, what is intelligence? We know human intelligence or anthropic intelligence, and through AI, we're trying to make new kinds of intelligence, but just how variable might expressions and faculties of intelligence in the cosmos really be? I think that this is a key question, and it'll be very important when we're looking for technosignatures, when we're looking for advanced technologies that are demonstrative in one way or another of intelligence. So I think that a very interesting prospect for SETI is the generation of hypotheses on non-anthropic faculties of intelligence through some sort of a rigorous method. So what are the possible, feasible, and really evolutionarily optimal ways in which intelligence could express itself? So just to kind of entertain you, I've come up with a couple of future hypotheses that we might want to consider. So there are scalar hypotheses. How large can an intelligent organism agent be? You know, it could be the size of an animal. Could it be the size of a planet? How large could an intelligent life form be? It might not be anthropically scaled. It might be larger. And how small could it be? Could there be an intelligent species that comes up with nanotechnology and is able to replicate, you know, very small but efficient computational agents? Those would be intelligent, but they'd be very small. They'd be kind of hard to find. There are also phenomenological hypotheses. So we have certain kinds of experiences as humans because our brains process information in a certain way, but that might not be universal. So we can ask, though, very concrete quantitative questions. You know, what is the maximal density of information storage that an organism could exhibit? What's the maximal?
Sorry, James, we need to wrap up. Thank you.
Sure. What's the maximal speed? How might organisms experience time? We can also consider more formally if there are other kinds of logical systems, symbolic systems, or mathematical systems that other organisms could practice. And in the end, I think that the physics of information can offer a very rigorous and interesting quantitative basis for doing this. And we can begin to consider not only what the possibilities are, but what would be optimal and what kinds of fit organisms could have different faculties of intelligence that we imagine could actually be able to survive in the cosmos. So thank you very much, and feel free to contact me at this email below. And for those of you who want some pandemic reading, you can screenshot the references, or I'll provide the slides at a later time. Thank you very much.
Thank you so much. Pandemic reading is always good, much better than Netflixing all the time. But if you were going to watch something, SETI Talks, there's February 18th one at Exoplanets. So they've been really fun for me to learn. Last but not least, we have Dr. Kimberly Warren Rhodes, who's an astrobiologist at the SETI Institute. So I'll pass that over to Dr. Warren Rhodes. Over to you.
Hi, everyone. One second, let me get, it says host disabled participants screen sharing.
Oh, Serena, would you be able to make Kimberly a co-host? I'm not sure if Serena's on, but okay, now you're able to.
All right, let me try it here. Perfect. All right, here we go. Let me just start that. Where's that? Oh, view.
And then just as Kim is currently pulling up her slides, we'll just do Q&A after instead of breakout rooms.
Okay, so I didn't realize I was the wrap up, but no problem. I'm going to bring you a little bit into the just nitty gritty of sort of what we do at SETI. I'm a field astrobiologist. I have a background in astrophysics as an undergrad, and then I have an environmental science and ecological and microbiological background for my PhD. I've worked in deserts throughout the world, and my job right now is to try and understand. We're getting, as Natalie Cabral brought in a very nice introduction for my talk, on how do we actually, now that we're going to be going to some of these planets to look for life, are there more efficient and optimal ways to do that, to answer some of these larger questions? But, you know, we have a very specific problem we need to look for and train rovers to look for life. And so one of the possibilities is to learn from analog environments, things that are similar to Mars or Europa, and see, are there patterns and predictability that we can use to optimize the search for and detection? So one of the big questions, and many of you have touched on it in astrobiology, is, are we alone? Is there other life in the universe? And the question for me as a field scientist is, and particularly looking at microbiology, because that's much of what we will be looking for on some of these planets when we do land, is, are there patterns? Is life just random and then there's no predictability to it, or are there patterns? And this is one pattern from one of our examples that from the United States, from the space station at Christmas. You can see a pattern for Homo sapiens. On the left are desert flora. The top left is the Mojave Desert with plants filling cracks that hold water. And down below is a plant pattern in deserts that is generated, you know, organically, but it basically concentrates water. On the right, you see in the upper, upper right, this is the Great Salt Lake in Utah, and the red color is not random. That is from what we call halophilic bacteria. That is a sunscreen they use to survive. And down below, here they are, these halophiles, that means love living in salt. This is a little water salt inclusion where organisms live. And here you can see sort of the red coloring of that. All non-random patterns. I love this one. I lived in Hong Kong and did a lot of work in Western China deserts. And this is obviously a non-random organismal pattern generated by humans as cities. And so I modeled this in terms of inputs, outputs, waste, and different things. But again, 7 million inhabitants. And likewise, in that same little fluid inclusion, there are non-random patterns. We have 7 million inhabitants in this small little fluid inclusion that's only a few micrometers wide. And one of my other favorites, the Penibacillus vortex, that generates this pattern, thousands of bacteria circulating around a common center. So these are examples of what we don't believe are it's not a random pattern. Now we get to the ground, into the field where I do most of my work. And we're getting to a more specific scientific question, which is microbial life random in the driest and coldest deserts on Earth, because we work in those analog environments, as Natalie Cabral mentioned, to prepare ourselves for some of the instrumentation and exploration strategies to get to Mars. Again, here is this is actually, I hope you can see it. It is on the right, you can see sort of it's called a biological soul crust. If any of you have been in Death Valley or Mojave, you'll have seen these before. And on the left is a biological soul crust in the Atacama Desert. And we are trying now to map these patterns and understand how they're generated, and if they are random, are they predictable, are they explainable? And so we use some of the rover technologies. This is a panoramic stereo visual image of some of the habitats that are in this desert. And we then do visual images of them. We also take spectral analyses to look at their chemistry and their mineralogy. And then I go in with other biologists, and we then explore and basically map in excruciating detail what areas have life. And in this particular example, it is cyanobacterial life that is visible to spectrometers and to the human eye. So in that last picture, this is like the first cut of what we call a heat map for life. And in the red are areas that have higher biomass. The yellow is moderate biomass, and the blue is very low probability of finding life. And these are tied to water availability in the environment and to particular types of what we call microhabitats, meaning different kinds of chemistries in the soils. This was just another example. This is what the visual looks like. And then we also did spectral images. And then if you can see here, the green and the yellow, this is a very large microbial hotspot tied again to particular kinds of chemistries and water availability. So in quick, very lightning speed, we have answered some questions. One being, many patterns in life are not random. We found this in deserts, in the troposphere, that we thought all was randomly, a lot of random microbial organisms being generated and moved across the planet. We're finding there are structure to these microbial communities. In the human gut microbiome, it is not a random assemblage. And these have very large impacts on human health and hopefully what we think on astrobiology. Because biology forms non-random and distinct patterns and hotspots, and these patterns can be explained in many different ways, either through water and food availability, through habitat types, through, like, as I mentioned, cities. We can understand them and create a library of those patterns and hopefully use AI and ML to model them. And as well to generate algorithms and templates for searching for life on other planets. And that is basically like generating, in the old pirate days, a key to a treasure map. And so here are some of the patterns. This was an AI generated pattern for some of that grass, the desert grass that I showed earlier. And on the right, we're looking at microtopographical changes to see if that gives us clue about how the biological soil crust patterns are generated. Implications for Mars and other ocean worlds is that on Earth, at least, and that's the only example we have right now, microbial life does, and life, and some of the other talks were really interesting. However we define it in terms of terrestrial, it does organize itself in some circumstances in predictable patterns and habitats. And we can use this to reduce the search space and effort, which is a key goal of astrobiology, and that streamlines cost and time. So if I had given you this picture of, this is one of the analog environments we work with in Chile in the high altitude desert, and I asked all of you to pick, this is the challenge, pick 2 spots that you've never been there to go to and search for life. You only get 2, and it's a very costly, a very time consuming way to do this. Would you be able to do it in the most efficient and hopefully prioritized manner to be able to find life? And our results basically show that once you can understand at least certain patterns in the underlying, you can then make sense and decode the environment in a very particular way that may be a very useful blueprint for, here's our little rover, so that when we enter that space.
Hi, Kim, we can just
No
wrap
problem.
up, sorry.
Yeah, no, this is it. This is the blueprint for automated robotic search for that environment. So the red environment now is the highest priority that you would send that rover to. And then we can do this from orbital all the way down to the microbial scale. And just so the wrap up for everybody, we are all humans, non-random as well. You can see this is one of our field sites, and we are underneath the, in an intense, in a very non-random pattern out in the middle of the desert. Thanks, guys.
Thank you so much. I want to say I'm just so inspired by all of our speakers, and I think, you know, these talks are meant to pique everyone's interest and their curiosity so that they can explore more. And the wonderful thing for those, especially for those of you in the Bay Area, is that the SETI Institute is actually located in Mountain View. And while right now everything's virtual, I highly encourage everyone to continue their explorations even beyond these talks. Now, with that said, we'll go into Q&A, and I know there were many interactions on the Q&A already, but there is a Oumuamua. So I might not be saying this properly, but I'll just leave that word there and see and pass it to our speakers to talk a little bit more about this, because there seems to be a lot of interest.
Well, I can start, and then some of our more qualified scientists can weigh in. But Oumuamua has certainly been very interesting, and as many of you may have noted, Oumuamua has had a lot of attention in the media recently because Harvard astronomer Avi Loeb has made statements suggesting the possibility that Oumuamua is in fact an alien spacecraft, or, you know, a technological phenomena rather than a natural phenomena. And of course, that has been a highly controversial perspective from his part, and many of his own colleagues in the astronomical community are highly questioning his analysis leading to that. But nevertheless, he's based his observations, or his I wouldn't say conclusions, but rather his speculations, on observational data. He's mathematically quite rigorous, and he's looked at the Oumuamua phenomena in terms of different characteristics. I mean, it was pretty well clear that this was not a comet. It didn't behave like an object that was ablating material from its surface as it passed by the sun, which, if it were, when it went around the sun, might explain what has been observed as an acceleration in the Oumuamua object as it left our solar system. And one of Avi's observations was, well, if it's not ablating material, as comets do, which would give it the effect of propulsion to eject material from one side of the object, how do you explain that the object increased its speed as it exited our solar system? So different anomalies in the observed behavior of the object gave rise to his speculations, or his perspectives on the Oumuamua object. It also, from what we can observe from the rather minimalist, I mean, we're talking about pixel level data, observational data on the object. Nevertheless, we can tell things about its spin characteristics, and a little bit about its shape, because of the way it reflected light and not reflected light as it tumbled through space. And some analysis that seems to be indicated with about a 90% level of certainty suggests that the Oumuamua object, while long and thin, was also flat and disc-like in its shape, like a pancake a little bit, rather than the cigar shape that has been commonly illustrated in pictures. And of course, realize that the pictures in the newspapers have nothing to do with observational data. They are simply artist interpretations of what scientific observations have indicated. So anyway, we think Oumuamua is wonderfully exciting. If for no other reason, people are talking about it. So what I love about the fact that Avi Loeb is out there with controversial hypotheses is that it gets the Oumuamua, removed from the back pages of the newspaper to the front pages of the newspaper, and makes it a topic that people are excited about and want to talk about. And, it's kind of a refreshing distraction from some of the topics that have dominated news in the last month or so. And so I think it's very exciting and very positive from that point of view. It's great to see science stories, even controversial ones, getting attention. And I don't know if Nat or Dana or anybody else wants to weigh in more on this, but it's a fascinating object and subject, and of course also very rare in terms of, we haven't observed very many objects that have come from literally from interstellar space, from some other system into our own solar system and left again.
So can I say something?
Sure, Carol.
Yeah, so this is exactly the kind of thing I'm talking about when I talk about anomalies. That is to say, it doesn't easily fit into the description of a natural large space body, and it also doesn't naturally fit into a description of something that we would expect, given our knowledge of Earth intelligence, so, and the kind of technology we have. So I think the fact that Loeb and others are pursuing it, and initially I did kind of keep track of this because I'm going to use it in my book actually. What I think is really interesting about it is that initially it was just immediately rejected because people could think of these kind of fantastic ways in which they could fit it, stuff it into the non-natural category. And this is a tendency that people have. Let's get something that really fits tightly with our expectations. And I don't think, as we go out and look at the universe for things where we're basically generalizing from a single Earth example, that we're going to have much success if we aren't open to, hey, this shouldn't be here. This is weird, and we ought to explore it in more detail.
Thanks. Can anyone comment on how thoroughly it was observed? That is, how many, pictures we have of it that would allow us to accurately estimate its track? Is there any possibility, for instance, that the observations are just too vague, and when we refine them, we will decide that in fact the orbit wasn't anomalous?
I think from what I understand, and maybe Dana can weigh in here because he's actually an astronomer, that the observational data is pretty clear on the trajectory of the object and the speed of the object at different points along its path. It's again, a lot of the information about it is inferred from the so-called light curves, or the patterns of reflected light as this object traveled through its trajectory. And so that's how we infer things like, shape and size and the different reflectance attributes that the object had. But I don't think we're going to find that what we believe to be its trajectory is incorrect, or that what we believe to be, its measured velocity at different parts of that trajectory is incorrect. But we'll certainly, we may learn a little bit more through the data, but the data is very sparse. Again, I think we're talking about light curve data on observational images that are like a pixel, literally. Dana, do you have any more to add to that?
Yes, it was never more than 1 pixel. But the positions were many well-sampled, highly precise positions. It's absolutely unambiguously an extrasolar object. No question whatsoever.
Yes, sorry, to add to that, the shape of the asteroid is atypical for a shape of an asteroid in our solar system, and is an extrasolar system object visiting us. So those the main 2 evidence. But what it was, we don't know yet. We also have another extrasolar system visitors, like comets, but those are very well defined, and they are very similar to the comets we have in our solar system. So that's the reason Huma was taking, like this can be something out of our comfortable box of objects that we have studied before.
Well, I'm surprised I haven't heard much speculation about where it might have come from. Can you track back its trajectory as it entered the solar system to say what stellar systems it might have originated in and how long ago? We could be talking billions of years, of course. But
sure. I don't know, Dana, if they've done analysis of its path in terms of potential source.
It doesn't come from anywhere. The stars are moving as fast as it was moving, and it's moving a speed of relative to the sun of a parsec in 100,000 years. So running its trajectory back doesn't lead you to anywhere. You don't get any information, unfortunately. But its motion was like the stars in the solar neighborhood. It was not extragalactic. It's clearly not extragalactic.
Okay, thanks.
Other questions?
Obviously
Cervantes,
a fun topic.
Yeah. There was also another question about, are people studying microbes that live in rock deep below the Earth's surface and looking for similar microbes on Mars?
Nat or Kimberly?
Yeah, well,
Yeah,
I can get started.
Go ahead, Natalie.
The micro person is Kim, but in terms of environment, yeah, we know extremophiles that are living within kilometers in the crust of our own planet, and so they have very different metabolism and they have different type of energy. They are actually extracting their energy from the radioactivity of the rocks, so it's very, very different from the microbes that we have at the surface. And it is very possible, and this is something we think about Mars, because very early on the conditions for that were favorable at the surface of Mars disappeared, obviously, and we had lots of radiation coming down, and very short radiation. So there are a number of hypotheses. The first one is that life never appeared on Mars. First, if it appeared, we have to realize that it took 88% of the history of our planet, of our own evolution on Earth, to get to complex life. And so conditions being favorable on Mars at the surface for so little time, and then Mars being smaller, having less mass and less energy, cooling off much faster, then we have to think about microbial life and nothing else for Mars. So if we had microbial life, either it was at the surface at some point and disappeared when conditions were disappeared as well, or it migrated down into the subsurface. And another hypothesis is that life on Mars was never at the surface at all. We still have question marks about the origins of life on Earth. Some people still hang to the hypothesis that it was born deep into the oceans, which protected it at the time of the heavy bombardment. There is a new theory that departs from that says that life never was at the bottom, never started at the bottom of the ocean, but rather in the tidal environment with shallow waters where the energy could be accumulated from this tidal environment. But regardless, there is a possibility that life never had any contact at the surface on Mars. And then it would have been protected in a fairly continuous environment over a billion years. And there is a sort of a conveyor belt of water and energy and nutrients on Mars that's not at the surface anymore, but still exists deep into the subsurface. So definitely the Mars life on Mars in the subsurface is a great hypothesis and something that we can document. I don't know, Kim, if you want to add something to it.
No, I think you did a really good job of that, Natalie. But I guess the only other thing I would mention is, as of yet, really, we haven't found a speck or inch of the planet here that doesn't have some form of microbial life, including deep in the. There are some controversial studies that have shown possible areas, like areas that where you double on you have a very low acid and you have a very high salt. And so you have multiple conditions and that makes it much more difficult, but those are still a little controversial. And definitely in the deep subsurface, there has been a wealth of a surprising wealth of organisms, microbial communities found deep below in South African gold mines, in very deep fossilized salts in the UK. And so, yes, we're working on some of those things, but it's still, we know about this much about the microbial world on our own planet. Even, to be able to even generalize, we are unable to do that,
The concept of life under the surface is also studied in Europe moon and Enceladus moon in Jupiter and Saturn.
Yeah. Other questions? Looks like a couple have popped up.
Yeah, I saw one with the meteorite, the Martian meteorite. I can address this one. And so there are a number of Martian meteorites on Earth. And that leads to the interesting idea, which is documented now, of planetary exchange in the history of the evolution of those planets, which means that very early on, we had lots of comets and asteroids bombarding planetary bodies as they were accreting. And so material was flying around all over the place. Although this bombardment has substantially decreased and the size of the impactors has decreased too, it's still happening. And the Martian meteorite is 3-some billion years old. So it's not 4 billion years old. It's a little late. It's in the tail end of the heavy bombardment on Mars. And then, so you are asking about these little pockets of rocks in it that look like bacteria. You're talking about the Allen Hill meteorite. And so there was this controversy. It was, in fact, a wonderful scientific debate. And I was very close to that debate because David McKay, who brought the idea, the hypothesis that what we were seeing in the Martian meteorite were indeed bacteria and signs of life on Mars, was not only a colleague, but also a friend. And we had long discussions about that. I was skeptical, but he was very passionate about that. And what I'm saying usually for the Martian meteorite is, well, one thing is for sure, is that we won't have the answer for a long time. But what it did an incredible service to science and to biosignature detection and to the search for life beyond Earth, because as we were asking those questions, having converging evidence of something, or visual evidence that something looks like something we know, we can put in a box and say it's a bacteria, or but wait, there are also rocks that look like that. So is it biological or is it a geological evidence? And this debate went on forever. It was actually a show at the Lunar and Planetary Science Conference. Every year, there were special sessions for the team who were saying this is a fossil, and the other one that was coming with counter argument. That went on forever. But we don't have the answer. But what happened with that is that more money was poured into developing instrument technology, increase in resolution. We now had something we could look at and say, what would it take for us to finally have an unambiguous answer to what it is? So that's my answer. Frankly, I am not convinced that we saw bacteria in them. It looks very much like the structure of the rocks, just interestingly enough, also look like some magnetic bacteria. But then you have to think, what are the odds that Mars, although with a similar environment or very close to it, would develop life that looks exactly like the one that we have on Earth? Might be the case because this is very primitive life. And I think that beyond bacteria or this type of bacteria, I am also one of the proponents to say that the universe might be full of green and blue algae and cyanobacteria because this is the easiest stuff and the earlier stuff that you can develop on the planet. So maybe Dave was right. We still don't know, but this kind of question, the same way as Uma is helping us, in fact, even through a lack of answer, to make progress in the search for life beyond Earth.
Great.
Thank you so much. I think Cervantes has his hand raised. And by the way, thank you so much for all the speakers and also attendees who are staying 30 minutes past the session. Clearly, there's a lot of engagement, a lot of interest. So thank you all. But I also want to be mindful of those of you who do need to go. Please feel free to, because it is way past the time. But yes, Cervantes, please.
Thank you, Wendy. Amazing session. I'm an MIT graduate, and I was watching with my son. This is very amazing session to provide general public about the science about the Earth, outside Earth. Yeah, my question really to maybe Bill Diamond. My question is really, I feel a lot of people feel look at History Channel, look at Asian astronaut theory, and then things like a lot of evidence, even in the past, even today. And then some of them even talk about we're using some alien technologies in our current spaceship, different technology today. So a lot of countries, maybe they have access to, but the general public always kind of get guided, say there's no such thing. But we feel there's a way people already know, but is that a correct observation? Some people already know there's access, they are talking, they are really using the alien technology to advance our human technology today. Yeah, I know it's very controversial, but I know it's like it's a science and then general public. I don't want to hold anybody against I just want to really hear about this. Thank you so much.
Sure. Well, I mean, it's of course a topic of great interest to lots of people. Is there evidence past or present? I mean, are UFOs signs of life or intelligence or alien visitation? Are things like the pyramids or current technologies? I mean, I think for the most part, serious science has sort of debunked a lot of the ideas that the pyramids were built by aliens, or that Stonehenge could not have been done with with available technology. I mean, I think that if there were any advanced species that had the technology to get to Earth from some other stellar system, when you take into account the distances we're talking about, they would probably have had the technology to do something a lot more sophisticated than the pyramids or than Stonehenge, quite frankly. It seems that most of the technology we take advantage of today really has the ability, when you look closely at it, you can trace back its evolution and its development through invention and discovery over time. So there's really not strong evidence to suggest that any current technologies we're using really have their roots in some visitation. One thing that I think is always kind of fun to and important to remember is again the scale that we're talking about here. I mean, our closest neighbor planet, neighbor star system is Alpha Centauri, and there is now, we know, at least around Proxima Centauri, an exoplanet has been identified, but this is 4.2 light years away. This is our closest neighbor. The fastest spacecraft that mankind has ever built, at least going in one direction, is the New Horizons spacecraft that flew past Pluto in 2015 and flew past that other outer solar system object just last year, a year ago or so. And, it's traveling, I believe, at about 40,000 miles per hour. We've built faster spacecraft, but they're only faster because of the gravitational assist they get as they orbit things like the sun. Like the Parker Solar Probe is going much, much faster. But if we took the New Horizons spacecraft and aimed it at Alpha Centauri, it would take 17,000 years to get to that closest neighbor with our current propulsion technology for the fastest rocket we've ever built. So bearing that in mind, even if somebody has orders of magnitude greater speed, you're still talking about, at least in terms of transporting biology, at least biology as we can imagine it or not imagine it, multi-generational spacecraft, which by definition would also have to be very big and pretty hard to hide. If there's a technology that's advanced enough to have figured out how to, say, fold space and time and not worry about those great distances, they probably also have the technology not to be seen by Navy pilots if they don't want to be, or by anybody else for that matter. So I think there are some kind of logical thought experiments you can undertake when you start thinking about scale and other problems that tend to at least raise questions when people look at phenomena they don't understand. I think Carol was saying this earlier. There is a tendency, of course, to explain the unexplainable in ways like, well, let's blame it on the aliens. I mean, over history, and we used to do that. We used to explain unexplainable phenomena that we didn't understand by attributing it to gods or deities. There was a god of lightning and a god of thunder and a god of the sun and all of these things. And now that we know pretty much that, that's not the way nature works, we still have anomalous things that we don't understand. And we say, well, it must be the aliens. So it's a natural tendency and kind of interesting. Of course, I'm at a place where we certainly like to believe and do believe that there's not only life beyond Earth, but probably somewhere in space and time, intelligent technological life. But have we been visited? Are we being visited? The evidence to me isn't so strong. Nat, looks like you wanted to weigh in on that.
To add, I think you covered that very, very well. I would say though, and you mentioned that a little bit, I would step away from anthropocentrism, which means that, we tend to think about distances and things like that with what we're capable of doing. So we're still very limited right now. So let's for a minute think that these aliens, they figured it out. They can come from 13 billion years, away in no time and be back home for breakfast. So let's figure this out. You have to imagine that if you are a very evolved civilization, you probably are not going to stop by our little blue planet and stack up stones just to say, hey, you know, I was here. Here's a pyramid and figure it out in 4,000 years from now. Or you are just not going to zap cornfields to make crop circles. There are probably a lot more than to it. You first have to, you know, put reason into those things. Also, I think that Bill is right in saying that extraterrestrial ET and UFOs in particular are taking the place of old myth. In past times, we tend to explain with, you know, extraordinary tales, and this is how mythology was created and myth. And aliens are, in terms of how ancient astronaut theorists seeing them, is a myth. It gets your imagination going, etc. So there is that. Plus, I think that we have to give credit a little bit to our own species. And when you are talking about, you know, UFOs and things that we don't understand, I would say that a substantial part of it, the myth, is probably entertained by people who have an interest of, you know, maintaining it. And by that I'm saying is that there are people working on very advanced technologies. They are not alien, and they are probably government agencies. And they prefer you to believe that this is an extraterrestrial something than try to start and figure it out what is going on and documenting a little too close what's happening in the technologies that we're developing. And as far as flying saucers are concerned, because now we have this Freedom of Information Act and a lot of documentation is being released, we are learning more and more about how close from disaster we came during World War II. Because the Germans were extremely advanced in terms of propulsion, in terms of what they were trying to test, just to maybe save the day in a Hail Mary to start still, you know, to win the war at the end. And these documentation are showing many attempts at anti-gravitational propulsion in terms of craft that look like exactly the flying saucer of your folklore, which is this disc shape kind of things. So knowing that the Soviets and the US government got their hands on German engineers on both ends of the continents and on each side of the ocean, you can imagine that this technology has evolved in time. And that many of the things we cannot explain in the sky is probably not alien. It's coming from here, but we don't know everything. And I would say I am very open to, you know, I'd be the first one, and well, maybe the second, because Bill might be equally excited if tomorrow we say we have a genuine flying saucer that's coming from wherever, but we have contact. And something for you, and that will be my last comment on this, is that something that is very important for people to realize, to separate what is scientific talk from ancient theorist nonsense, is that science will always run through the hypotheses and come to the most extraordinary claim as a last resort. Whereas conspiracy theorists will start with the extraordinary claim and then ask questions and answer their own question as the statement for the next sentence. So you have to follow, you know, how this works. If you start with the extraordinary claim first, be careful. And please do your own homework.
I'd like to say something, just because I covered hypotheses. I think that SETI is actually a very good workout in terms of mental exercises, in terms of seeing how good you are at following the scientific method. And I'd say that there is this dichotomy between, you know, there's prestigious science and there's tabloid explanations. But I would say even within the sanctioned halls of academia, there's a wide range of hypotheses to which I would assign various, sorry, to which I would assign various degrees of credibility. There are some hypotheses in academia that I think are rather meek, and there are some that are actually quite strong. And it can be very fun to tease out what the consequences are of your hypotheses. For instance, maybe you think this idea of life assembling itself from very small parts just seems so complicated. I think one scientist said, you know, it's like the equivalent of trying to assemble a plane randomly from a tornado throwing parts together. So some people think this is unbelievably convenient that you've had life assembled this way. So some people say, well, maybe it's just easier to say that some other creature created it. It could be another alien species. It could be, you know, you name what you want to call it. And that seems more simple, but then you have to ask, well, where did that thing come from? And all of a sudden you found this recursive trapdoor, and you found that actually your model needs much more parameters than you thought. So in the end, I tend to prefer models that compress the things you're observing to a very small number of parameters. The more parameters you have to introduce into your model, the more messy it is. And oftentimes, especially when there's explanations for SETI where in the end you're saying, oh, we've found them, but here's all the reasons why no one talks about it. You're going to find that your thriller novel that you've concocted has a lot of parameters, many more parameters than, say, rare earth hypothesis. So I tend to use Occam's razor, very parsimonious, minimalist when I'm approaching SETI. I always try and make the least number of presumptions possible. I think it's helpful. And that's part of the fun of SETI is, you know, it's like you can exercise your imagination, but then you have to tame it. And it's that discipline about it that I really like.
Great. Well, Wendy, that's probably a fabulous way to wind this up, because I know we're past the top of the hour.
Yes, I know. I was just going to wrap it up, and I just want to say thank you again so much for all of your time and for staying way past the hour for all of you. I want to say again that, you know, this is only the beginning of our exploration. So please, you know, do look up the SETI Institute, and I'll share the slides with all the attendees after we post them securely. And then, I encourage you all to reach out to all of the speakers. Again, you know, their profiles are on the SETI website, and their emails are there as well. So please continue the engagement, and thank you all for your time.
Thank you. And thanks, Wendy, for putting this together. Thanks, everybody, for sticking around and listening. And thanks to all my colleagues who shared your time this evening. It was good fun. And we hope to see you guys again for more discussions.
Okay. Bye-bye.
All right.